Okay, we're going to talk about VSEPR theory, and this has to do with the shapes of molecules. VSEPR stands for valence, shell, electron, pair, repulsion theory. That's a mouthful, and so we just say VSEPR. This is based on the idea that electron groups are going to repel each other. It's a very simple model for molecular shapes, and it works pretty well. So here's the idea. On this central atom, there are 3 electron groups. There's a bond with this atom, and a bond with that atom, and a bond with this atom. These pairs of electrons repel each other. So they're trying to get away from each other. We need to understand what is an electron group. An electron group is not the same as a pair of electrons. It's not an electron pair, it's a group. It could be more than 2 electrons. So a lone pair is an electron group. A single bond is a group. A double bond is 1 electron group. A triple bond is 1 electron group. Or a single electron, like you would find in a free radical, is 1 electron group. So we're looking at groups and how they would repel each other. We're just going to look at repulsions on interior atoms because those are the only ones that affect the geometry. If we look at how the electron groups on this terminal atom, repel each other, that has nothing to do with the geometry, so that's just really a waste of time. We're only going to look at ones that are in the inside. So the preferred geometry for a molecule is one that has maximum separation of the electron groups. This is going to be the lowest energy. So I think of it a little bit like this. So say you have, I guess in this example, we'll say this is you, and this is one person you dated a while ago, and this is another person you dated a while ago, and it ended badly. And so you really hate this person, you really hate that person, they hate each other too. And so this is the Earth, and you want to get as far away as possible from these people, right? So you're taking up positions, as far away as possible. If there's just 2, you could be on opposite sides. But if there's 3 of you, then opposite sides, somebody's going to have to be close. So you're going to spread out. So that's the idea, is thinking of spreading around a 3-dimensional sphere, however many things, trying to get away from each other. It's a little bit like children in a minivan, right? Don't set them right next to each other in the back corner. You want to spread them out, give them as much space as possible, minimize the whole he's breathing on me thing, right? It's so annoying when someone breathes on you. Can't you tell him to stop breathing? No, I can't. So let's look at beryllium dichloride. We need to look at the Lewis structures. This is all based on Lewis theory. So beryllium dichloride. So beryllium is one of those little guys that violates the octet rule. And so I'm not going to go over how I'm drawing these Lewis structures in detail because I just did that in the previous chapter. Here's the Lewis structure for this. What we do here is we look at the central atom and we ask ourselves, how many electron groups are attached to the central atom? Well, here you have a single bond and a single bond. Each of those is 1 group. So we have 2 groups. So then you think, how did 2 groups get away from each other? Well, they go to opposite sides. So if beryllium is the Earth, this chlorine is going to be on one side of the Earth, and that one's going to be on the other, as far away as possible. Does that make sense? And then we talk about a bond angle. So the bond angle is from one atom to the central atom to the other atom. And here the bond angle is 180 degrees. It's a straight line. So we say that this is a linear geometry. The 3 atoms line up. They make a line. This is confirmed by observation. Beryllium dichloride does have this shape. It's linear. Any questions? Let's look at CO2. So if we look at CO2, again, we need to look at the Lewis structure because lone pairs on the central atom are going to be a fairly big deal. For CO2, There are no lone pairs on the central atom. There's a double bond here and a double bond there. A double bond is one group because covalent bonds are localized, at least in Lewis theory, between these two atoms. So these two double bonds can't get away from each other. They're stuck. They're fused together, essentially. So they're stuck. So it's this double bond trying to get away from the other double bond. Two groups, again, linear geometry. This time, though, it's two double bonds instead of two single bonds. Same result. BF3. Again, you've got to look at the Lewis structure. Boron is one of those guys that often is happy with an incomplete octet. And so we did this one earlier. This is the Lewis structure. How many electron groups on the boron? 3. 3 single bonds. Each single bond is an electron group. There's no lone pair on the central atom. We don't care at all about what's going on with the fluorines. It doesn't matter. 3 groups. How do 3 groups get away from each other? Well, now they have to spread out a little bit. You can't just be opposite because that would mean that somebody else is going to be too close. And so it's going to make this trigonal planar geometry. So this is a triangle. See that? It makes a triangle. Planar because it's flat. Okay? The maximum separation there is going to be 120 degrees. So that's not as large as 180, but with 3 things, that's the most you can get. So that's trigonal planar geometry. So now I'm going to show you the balloons. And unfortunately, I can't do that for the internet people. Formaldehyde also has 3 groups. Here's its Lewis structure. There's carbon, single bonds to the hydrogen, double bond to the oxygen. Still 3 groups, though, because a double bond is one group. So 3 groups, trigonal planar, they're going to spread out. The angles here are going to be slightly different, though, because the double bond is a little more repulsive. It's bigger, bulkier, it takes up more space. So you can kind of imagine if one of the balloons was larger, it would push the other 2 slightly closer together. So we see in this molecule that this angle is a little larger than 120, and this is larger than 120, and then this angle between the 2 single bonds is a little smaller. You don't need to memorize how the, exactly what these bond angles are. You should know that a trigonal planar ideal geometry has a 120 degree angle. And then if you have a double bond, it's going to mess that up a little bit. I would expect you to tell me that this angle is larger than 120 and this one is smaller than 120. Okay? Because the double bond pushes the others slightly more together. Didn't come out very well. Okay, so I have blown up the balloons in class, but for the internet people, here are pictures of the balloons. So this is what happens with 2 groups. You get a linear geometry. 3 groups, you get a trigonal planar geometry. Okay, what happens with 4 groups? When you add that 4th balloon, that causes those other 3 balloons to be pushed a little closer together. They get pushed down. So this is a tetrahedron. It's 4 things arranged around a central point. That's a shape that we're not really familiar with, right? It's a regular 3-dimensional solid that has 4 triangular sides. So tetra refers to 4. So it's got 4 points, 4 sides. So the angle here is 109.5 in a perfect tetrahedron. So you should know 109.5. That's the angle of a tetrahedron. So what kind of molecules do this? Well, something like methane. So methane is CH4. We've got carbon with 4 single bonds. 4 groups make a tetrahedron. And so here we have a model, just like this one I have, of methane. It's a tetrahedron and it's got angles of 109.5. The Lewis structure looks flat. Lewis structures always look flat. They're easier to draw that way. This looks like there's 90-degree angles, but that's not the case. 90 degrees is smaller than 109.5. They're going to pop up and make this form. I can force these balloons into a flat shape, right? I can force them to be flat. They don't like it, right? And if I let go, they pop back into a tetrahedron, okay? Think about balloons when you try to think about these. What if we put in a fifth balloon? Let's do that. So you add a fifth group, and that causes the tetrahedron. You're pushing these four together and getting another one in here. And we call this shape a trigonal bipyramid. So if we draw this shape as a regular solid, we've got a triangle here in the middle with a pyramid on one side and a pyramid on the other side. So it's a triangular bipyramid as opposed to the triangular planar, which is a flat triangle. Here we have a model of that. So we have two different kinds of atoms attached to the central atom. And on my balloon, I color-coded them, right? So on my model, the red ones are called the axial atoms. Those are like the axis of the Earth, North Pole and South Pole, and it rotates on this axis, right? And then these are the equatorial, and they are around the equator of the Earth. So these are in a different position. Between axial and equatorial, there's a 90-degree separation. Between equatorial and equatorial, there's a 120-degree separation. So not all the angles are the same. It's just a thing of geometry. You can't make them all the same. You just can't do it any other way. This is the best way there is. So something like phosphorus pentachloride, you look at the phosphorus, it's got the expanded octet, 5 electron groups, makes a bipyramid, a trigonal bipyramid. Octahedral geometry, let's add another balloon. So we stick a 6th balloon on there, and now we have what's called an octahedral geometry. If you make a solid out of this, you get an octahedron. It's got 8 sides. All of these angles are the same now. They're all 90 degrees. So you could still think of axial and equatorial, except they're all the same, so you don't really need to. So in my balloon model here, I've got the little girl wearing red with a white tutu. But now it doesn't really matter because the bond angles are all 90 degrees. So that's an octahedral geometry, something like sulfur hexafluoride, 6 groups. Any questions? So we should be able to determine the molecular geometry of a compound, of a molecule, just given its formula. So here we've got carbon tetrachloride. The first thing you have to do is do the Lewis structure. So carbon tetrachloride, we'll put carbon in the middle and attach the chlorines. And then you have to count up the number of valence electrons and make sure that you've got a good Lewis structure. So it's going to look like this. Once you have the Lewis structure, I know I did that really fast, then you look at the central atom. You ask yourself, how many electron groups around the central atom? 4 single bonds. So 4 electron groups, what do 4 balloons do? Tetrahedron. Okay, so they're going to make a tetrahedron. That's a good question. Why put the valence electrons on the chlorines? Because you got to make sure that you've got the correct Lewis structure. So if you don't do the full Lewis structure, you could end up like missing a double bond or a lone pair on the central atom. These lone pairs don't affect the geometry, but we need to make sure we've got the correct Lewis structure. Yeah. So it's going to be a tetrahedron. And so we could draw that like this, where this guy's coming out. No, that guy's not coming out. Never mind. Those are all in the same plane, and this one is coming out at us, and this one is behind. That's ugly. That's like my worst tetrahedron ever. But the molecular geometry would be a tetrahedron or a tetrahedral geometry. Questions like this will be multiple choice, and so you don't have to worry too much about the exact spelling. I know some of these words are kind of weird.